But along with this dynamics component, we have three main axes on which our activities stand. One is, of course, the dynamical systems, and by dynamical systems, I mean both engineering applications as well as non-engineering applications. Here we have given you some pictures of, for example, an aircraft and also flapping wings of a bird, which is to understand which you need to make MAVs, micro aero vehicles. You need to really understand the dynamics associated with this system. And this is what this figure also shows you, how the fluid structure interaction affects because of this flapping wings. That's one aspect. We also have other forms of dynamical systems like complex networks. That's the other axis. Here we are talking about, for example, very complicated systems like the human brain, which is made up of billions of neurons, and with each neuron behaving like a single dynamical system, and they're all coupled together through this network structure. Or, for example, the climate condition. If you want to model the Earth's climate, you have to model it as each measurement point being behaving like an oscillator, and they're all coupled in a network form. And this coupling actually, there's an interaction between each of these unit oscillatory units. And the next axis is the data science and machine learning. So this is something new that has evolved over the past couple of decades, where with the evolution of sensing technologies, we now have large voluminous data. And with that data, we have more knowledge about the system than just the physics associated with that system. So how can we utilize this data in building models and solving very complicated problems, which were earlier, it was difficult to solve. So this is the three main axes on which our research builds upon. Now, let us go to how are they connected. So to explain that, let us just go into the history of how the dynamical study of dynamical systems started. And this was started by around the 1660s by Newton, when he started investigating the dynamics of planetary orbits of two-body problem. So he was basically studying the movement of the Earth and the Moon. And through these studies led to the discovery of, or the invention of, the differential equations and calculus. But during the study, he had neglected the effects of all other planets. But when he wanted to include the effect of other planetary orbits, so, or in other words, want to solve a multi-body problem, he ran into difficulties, and that remained a difficulty till in the 1890s, when Poincaré came up with a geometric approach by which you can study in a different way. So he introduced the concept of phase space or state space. For example, when you have this pendulum, it's not just the displacement, but it also has velocity. And you can represent the dynamics in a state space defined by the displacement, that is a position, as well as the velocity axis. So this paved the way for study of dynamical systems in a different approach, and that also started the state space approach. And this was also the first time which enabled people to look into higher, more complicated problems. But over the next 1920s to 1950s, the focus was primarily on the study of nonlinear oscillators. Oscillators means it's a single degree of freedom system, which means the dimension state space is just limited to two dimensions, that is the position and the velocity. And the focus was on applications like radio, radar, laser. But in 1950s, the computers were invented, and that really gave an impetus in the study of dynamical systems. So once in the 1960s, Lorentz, who was a meteorologist working in MIT, he came up with a very simplified model for the circulation, for the atmospheric circulation, and that involved a set of differential equations which were defined in the three-dimensional states. And there he observed one day a very interesting phenomena, that if this white line was the integration that he was carrying out in his computer, and one day when he stopped the integration and then started it again with the initial conditions that he got, he observed that the trajectory was it initially followed the same trajectory, but then it started diverging tremendously. So this was the first indication of chaos that has been observed by, and also the extreme sensitivity to initial conditions. And this, of course, led to this. This is the figure of a Lorentz attractor, the famous work from his famous figure from his work. And there will be we have one of our colleagues is going to give a talk on what is chaos. So I won't go any further here. But the important point here is that one could observe chaos only one went beyond the two-dimensional state space. So subsequently in the 1970s, for example, people started to observe chaos in many other systems. For example, in 1970 May, chaos was observed in a biological system through some map. So iterated maps are nothing but some sort of a discretized version of a differential equation in some sense. Okay, so it was observed in chaos in there, and then we had Mandelbrot, who carried on his studies on chaos further and came up with these fractals and these beautiful diagrams, pictures. Then it really went on. Now, Ruel and Takens observed chaos in fluid dynamical problems. So here we have a picture where you can see the vortical structure of in the wake of an aircraft. And then chaos really became very popular in the late 80s and 90s, especially after the publication of this popular science book by James Gleick. So now people started to work on with chaos in more and more difficult problems with involving higher state dimensions. And people came up with more useful behavior of chaos, where, for example, in encryption. So then in the 2000s, people started to work with systems whose state space dimensions are really very, very large. Okay. So that led to the growth of the subject called network science. So what network systems imply is essentially there is coupling. And when you have a coupling, traditional reductionist approaches whereby which you isolate the system that you want to study from its environment and study it in isolation, those approaches really do not work, because as we can see from this figure where we have two pendulums which are connected by a common thread, the behavior of them is not as it should be as for a pendulum which is oscillating in isolation. So you have to consider the entire all the oscillators in together to really understand the behavior of this system. So here is some picture of a regular network. So a regular network means each of these nodes could represent a dynamical system, for example, and these connections are nothing but the couplings between the neighboring oscillators. But a regular network is one where the couplings are very regular, in the sense that the couplings are only associated with the nearest neighbor almost. Okay. For example, this is connected to only the nearest one. This red knot is connected to only the nearest one and the next to nearest ones. So this type of and you can study, for example, using this type of networks is like you can study, for example, wave propagation, which we know that wave propagation you can also study by through partial differential equations. But if you take this partial differential equation and you numerically want to discretize that equation and numerically solve, you essentially arrive at something like this regular network. But the network for certain problems, the coupling could not be, maybe slightly more complicated. For example, here we see that the coupling is not only restricted to the nearest network, but also nearest nodes, but also to some far nodes. But so you see that the network can become more and more complicated depending on the type of problem. So but this is still a very regular network in the sense that it is symmetric and so on, but it need not be. So that has led to studies of networks with different topologies. For example, this is a very famous figure from a famous paper. So this is a regular network where all the connections are very regular. And then in the small world network, you have certain connections. Most of the connections are regular, but there are certain connections which are somewhat different. Okay, and then you have a complete random network. So there is no the connections you cannot put in any orderly manner. Okay, and then in real life situations, it was found that not all connections are formed. See, when you have these connections, you form clusters. But there are certain, in real life situations, you observe certain connections, certain nodal nodes where there are a large number of connections. Okay. But a large number of nodes with very few connections. So these are called scale-free networks. And so examples of scale-free networks are, for example, how the connections are there in the social graph in Facebook, for example. Okay, so this brings us to the concept of random networks, small world networks, and scale-free networks. These are the three most popular networks that are used. And the random networks was discussed in 1959, for example, but the small world and scale-free networks was discussed only in the late 90s. So this is only about the topology of the network structure. But what we are interested in is the dynamics of systems who has this type of network connections. Okay, and that leads us to enables us to study very complicated problems. Okay, the third axis is of course data science, and as you can well imagine that with one of the key challenges is in how to determine this network. You can't really how do you define how do you model such systems? So obviously that has to depend on data, and we come up with what are called database models. Now database models, to put it very simply, what it means is that you collect data, do some pre-processing, cleaning up the data, do some pre-processing, do some feature extraction in terms of, and arrive at an input-output relationship between the input, which are in the form of a data, and some output measure. Okay. So here, once you have all this done, the relationship between the input and the output is more of a black box, and there is not much physics behind that. So in general, people are a bit skeptical on the use of this so-called database models, but database models have their uses, for example, in applications where it is difficult to come up with an analytical form of a equation to define the dynamics of that system. For example, if you want to go from point A to point B in the city, and there are several routes you can take, but the most optimal route is basically based on the data that you have and what is the condition of traffic, and then you come up with an optimal route. So there, I'm putting things very simply, but there are obviously much more to it. But this is one case of just a database model. But in many applications, we have some knowledge about the physics associated with the system, right? So for example, we know that for a particular problem, F is equal to ma, the Newton's law has to be valid. So for that, we don't need data. That's an additional data we have. So can we combine this additional data with all this additional physics-based information as well as the data and combine them together and come up with better models? And that is where we come up with this physics-based machine learning. Okay, so here is just a schematic. For example, we have in a problem, we have several parameters from x1 to say x20, x30, and so on. And there is a functional relationship between all of these parameters. So we can use data to come up with this functional relationship. Now, one of the key features in this physics-based database models is that what is the interpretability of these models that we arrive at. Now, for example, this schematic diagram that I'm showing here is you could form, for example, this function, which is a function of some n number of variables, could represent a constitutive relation. Now, from using the data through some regression analysis, we might be able to fit a functional form, and the what should I say? The coefficients of all these regression points may not have a physical interpretation, but the function it has a physical representation in terms of that it may represent a constitutive relation, right? And then the reliability of it. So if the model has to be reliable, this we must also include in this modeling the usual constraints that any physics-based modeling should satisfy. For example, the physical laws, the conservation laws, and so on. Okay. And of course, to do this, the data must be sufficiently rich in the sense that the data covers the entire spectrum of the space, and there's no noise or spurious data has to be eliminated, and so on. And of course, the problem has to be in a well posed. So apart from this, there are other issues like, obviously, in any sort of analysis, there will be uncertainties in the form of uncertainties in your data, uncertainties in your knowledge about the physics associated with the problem, or you may not be able to consider all the parameters that are the influence of the problem. You may just by not knowing, you may be leaving out certain parameters. So that's where all your uncertainties come in, and that's when you have to introduce stochastic modeling also as part of your models and analysis. But that's an entirely different level of work. So we will stop here. And using these models, we can now focus on the type of very complicated problems that we work on. So for that, I will stop here and I will pass on the information, this to my colleague, Professor Arun Tangirala, who will guide you through the next few minutes. Yes, Arun.
Thanks, Sayan. A very good afternoon.